Study about trigonometric equations. Consider the equations sin x equals 1 by 2, sin x plus cos x equals root 2, tan x plus sec x into 1 minus cosec x equals 3. These are examples of trigonometric equations. Equation involving trigonometric functions of variable are called trigonometric equations. Let us solve sin x equals 1 by 2. There are infinite values of x which satisfy the above equation. Some of the values which satisfy the above equation are x equals pi by 6, 5 pi by 6, 13 pi by 6, 17 pi by 6, and so on. We know that trigonometric functions are periodic and repeat after an interval of pi for tan x and cot x, or 2 pi for all other functions. For the above equation, if we make a set of solutions, it will be like S equals set of elements pi by 6, 5 pi by 6, 13 pi by 6, 17 pi by 6, and so on. These solutions can be generalized, forming an expression involving an integer n. Such a solution is called general solution. Now consider the open interval 0, 2 pi. The solution which lie in this interval are called principal solution. Therefore, principal solutions of sin x equals 1 by 2 are x equals pi by 6 and x equals 5 pi by 6. Theorem 1. For any real numbers x and y, sin x equals sin y implies x equals n pi plus minus 1 raised to the power n into y, where n is an integer. Let us see the proof. If sin x equals sin y, then sin x minus sin y equals 0, or 2 cos x plus y by 2 sin x minus y by 2 equals 0, which gives cos x plus y by 2 equals 0, or sin x minus y by 2 equals 0. Therefore, x plus y by 2 equals 2n plus 1 pi by 2, or x minus y by 2 equals n pi, where n is an integer. That is, x equals 2n plus 1 pi minus y, or x equals 2n pi plus y, where n is an integer. Hence, x equals 2n plus 1 pi plus minus 1 raised to the power 2n plus 1 into y, or x equals 2n pi plus minus 1 raised to the power 2n into y, where n is an integer. Combining these two results, we get x equals n pi plus minus 1 raised to the power n y, where n is an integer. Theorem 2. For any real numbers x and y, cos x equals cos y implies x equals 2n pi plus minus y, where n belongs to set of integers. Let us see the proof. If cos x equals cos y, then cos x minus cos y equals 0, or minus 2 sin x plus y by 2 sin x minus y by 2 equals 0. Thus, sin x plus y by 2 equals 0, or sin x minus y by 2 equals 0. Therefore, x plus y by 2 equals n pi, or x minus y by 2 equals n pi, where n is an integer. That is, x equals 2n pi minus y, or x equals 2n pi plus y, where n is an integer. We get x equals 2n pi plus minus y, where n is an integer. Theorem 3. Prove that if x and y are not odd multiples of pi by 2, then tan x equals tan y implies x equals n pi plus y, where n is an integer. Let us see the proof. If tan x equals tan y, then tan x minus tan y equals 0, or sin x cos y minus cos x sin y by cos x cos y equals 0, which gives sin x minus y equals 0. Therefore, x minus y equals n pi, that is, x equals n pi plus y, where n is an integer. Let us see an example. Solve the trigonometric equation cot x minus cos x equals 1 minus cot x into cos x, where x is not equal to m pi, where m is an integer. Let us see the solution. We know that cot x equals cos x by sin x. Putting this in the given equation, we get cos x by sin x minus cos x equals 1 minus cos x by sin x into cos x. This implies cos x by sin x plus cos square x by sin x equals 1 plus cos x. This simplifies to cos x into 1 plus cos x by sin x equals 1 plus cos x. Since x is not equal to m pi, therefore cos x is not equal to minus 1, which implies cos x plus 1 is not equal to 0. Therefore, we can cancel 1 plus cos x from both sides, since 1 plus cos x is not equal to 0 because we are given x is not equal to m pi. So the equation simplifies to cos x by sin x equals 1, which implies that cot x equals 1, which further implies that 1 by tan x equals 1. This gives tan x equals 1, which implies tan x equals tan pi by 4. Using theorem 3, we have x equals n pi plus pi by 4, where n is an integer. Let us see another example. Solve the trigonometric equation sin theta plus cos theta equals square root of 2. Let us see the solution. Here we have sin theta plus cos theta equals square root of 2. We have 1 by under root 2 sin theta plus 1 by under root 2 cos theta equals 1. We know that sin pi by 4 equals cos pi by 4 equals 1 by under root 2. So the equation becomes sin pi by 4 sin theta plus cos pi by 4 cos theta equals 1. Using cos a minus b equals cos a cos b plus sin a sin b. We get cos theta minus pi by 4 equals 1. We can write it as cos theta minus pi by 4 equals cos 0. Using theorem 2, we have theta minus pi by 4 equals 2n pi plus 0, where n is an integer. This implies theta equals 2n pi plus pi by 4, where n belongs to the set of integers.